Hello, and welcome to Acoustics Derivations. In this video, we will be deriving the wave equation for waves on a string, assuming small deflections or deformations from the equilibrium position. In other words, we're going to be deriving the linear wave equation for waves on a string. Now, in this top left, I have drawn a figure of our string with respect to an x and a y axis. The string is in green. I've denoted a small portion of the string with horizontal component delta x, vertical component delta c, where c is the deflection or the deformation from equilibrium position. In other words, it's the position relative to where the string would be if there were no waves in the string. So if it was just a straight string. I've also denoted that there are tensile forces on both sides of this string, denoted as T, and those act at an angle, or they act tangent to the string at that given point. So, for example, this tension is acting relative to the x and y axes at an angle theta x. Or I should say sine of theta x and cosine of theta x, but you get the idea. So we are also going to assume that the string has a constant linear density denoted as rho sub L. We're going to assume that the tension is constant. We're going to neglect bending stiffness for simplicity, and we are going to ignore elastic forces other than recognizing that the string needs to be elastic enough to be extensible. In other words, it needs to be able to actually be able to move up and down as the wave propagates through. So let's get into the derivation. So this derivation starts exclusively with Newton's second law. Particularly Newton's second law with respect to the y-axis. So if you think back to your freshman physics days, Newton's second law is the sum of the forces in, or just the sum of the forces in general is equal to the mass times the acceleration of your whatever you're looking at. So in this case, it would be our string. So we're going to look at Newton's second law with respect to the y-axis, which, if you remember, is the direction the string is moving. It either goes up and down in this figure, if you would, which is the y-axis. So we have the sum of the forces in the y-axis is equal to the mass times the acceleration in the y-axis, or relative to the y-axis. So what is the mass of the string? Well, the mass of the string is simply the linear density, and then it would be times the length of the string. But we're looking specifically at this particular element of the string. So the mass of the string is rho L times delta x. And I should mention linear density has units of kilograms per meter instead of kilograms per meters cubed, which is what normal density is. So these units check out. Also, acceleration is the second time derivative of position with respect to time. Just think back to either freshman physics, or I think it's even covered in calculus. Okay, so there we go. So we have the linear density times this length element, delta x, times the second derivative of position with respect to time. Now, what are the forces acting on this? Well, the primary force is the tensile force. So we're neglecting things such as gravity, again, and anything else that you might consider. We're ignoring that here because they do not play a significant effect, or even they don't play an effect at all. Um, for example, gravity, if you think, just visualize in your head an oscillating spring in that's horizontal, and then you make it diagonal, so one end is higher than the other end, the wave still acts the exact same. So gravity doesn't. If the string is light enough, right, the gravity won't play um, an effect. So we're going to ignore it. So the only forces are tension. So we have and we have the tension at one end of this element and tension at the other end of the element. And now we're looking at some of the forces in the y direction. As such, we want only the vertical projection of tension, which is, think back to a triangle. It's the sine of the angle here, the way that I've drawn it. So it's um, tension times sine of theta of x plus delta x minus tension of sine theta of x. Okay? So that's the vertical projection of tension on this side minus the vertical projection of tension on this side. And this side is positive just because the way I've drawn it. And the other side is negative. It's going, it's going down. This side's going up, this side's going down. Okay. Well, I said at the beginning that we have small like deflections or small deformations from the equilibrium position, which means these thetas are quite small. So we can do a Taylor series expansion of sine of theta about 0. So about theta equals 0. So that's could also be called a Maclaurin series expansion. Well, if you know your Taylor series expansion for sine, you know that it's theta minus theta cubed over 3 factorial plus, and then a higher order term. And that's actually equal to theta if theta squared, the absolute value of theta squared is much, much less than 1. Why? Why is this true? Well, if you factor out a theta here, we have theta 1 minus theta squared over 3 factorial plus some higher order terms. If theta squared is much, much less than 1, then 1 minus much, much less than 1 divided by 3 factorial is even smaller, so it's basically 1. Okay, so we can rewrite this expression or this equation, replacing sine of theta with just theta. So let's do that. And now let's divide both sides by delta x. And I'm going to factor out tension here. Oops. Theta of x and divided by delta x. Okay, lovely. Now, let's take the limit. Take limit as delta x goes to 0 on both sides, but there's no delta x on this side, so it's just on the right. And, well, if you think back to your calculus days, this is the definition of a derivative. We have the linear density times the second order or second derivative of position with respect to time is equal to tension times the derivative of theta with respect to x. And I've dropped the explicit x dependence now. Okay, that's good and all. That is a valid, perfectly valid equation. However, we like to formulate our wave equations in terms of the wave variable. And theta, in this case, is not a wave variable. So so Cassie is. So we need to figure out a relation between theta and Cassie. So what haven't we used yet in this problem? Well, we haven't used the actual geometry of the problem yet. So let's appeal to geometry. Okay. We see that tangent of theta, looking at this right here, if I can highlight it here, looking at in this region right here, that tangent of theta is equal to delta Cassie delta over delta x. And if we're looking at an infinitesimal element as we did before, because we took delta x to 0, this is this delta Cassie delta x goes to the partial of Cassie with respect to x. Okay. So we're almost there, but now we need to once again do a Taylor series expansion, but this time of tangent of theta. So tangent of theta, if we expand about theta equals 0, is, I believe, theta plus theta cubed over 3 plus some higher order terms, which once again is equal to theta if theta squared is much, much less than 1. So we have a new relation that theta is equal to the derivative of Cassie with respect to x. Okay, so I'm going to erase here on the left because we need a little bit more space. Okay. So now let's plug this in right there. So we have linear density times the second order of position with respect to time. It's a terrible Cassie. Let me fix that. Is equal to tension times. We're plugging this derivative in for theta, not for the theta derivative. So we have to retain that derivative, and we obtain the second derivative of Cassie with respect to x. So we're almost done. Let's divide both sides by the linear density. And now we can define the speed of the wave as c squared is equal to tension over linear density, or c is equal to the square root of tension over linear density. So then we plug that in and we obtain our wave equation. Oops, I had dropped a 2 there. Let me fix that. There we go. And so this could either be written in this form or this form. So here is the wave equation for waves on a string, assuming that the deflection of the string is small. Thank you.